Okay, so hopefully you've all built your models at this point. And so what we're going to be doing today is talking about how you can prove that your model is similar to the actual monument. And that's going to be the first question that you answer. Is your model similar to the actual monument in every way? And I want you to really think about that question. And I want you to think about, is your model exactly to scale with the actual monument in every conceivable way? So not just the height and the width and depth of the base, but also, right, think about like a point like halfway up on your model. Would that be to scale with the actual monument? Think about like all the different shapes that you could use or that you could draw onto your model. Are all those shapes congruent to the actual monument? And so we'll kind of talk about how to think about that in today's lesson. And so if the answer to that question is yes, you're going to prove it with the flow chart on pages 3 and 4. And if the answer is no, like mine is, then what you're going to do is alter the dimensions a little bit so that they are similar, and then you'll prove that they're similar on pages 3 and 4. So that's going to be the first thing that you do if anything's not similar, is you're going to say which parts of the monument are not similar, then you'll change the dimensions. Then what you're going to do is post some pictures of your model right here, and then you'll write a flowchart proof here. Now you'll notice I gave you like 8 pages to do the flowchart proof. That's just so that you have room. If you want to put it all onto one page so that it's all neat and organized, that's fine. I kind of do both. I do my individuals, do it on individual pages, and then I combine all my pages together at the end. Okay, so here's a picture of my model from one side. Here's a picture from another side. You can see it's kind of tilted a little bit here. And then here's a top-down view. Okay, so the first thing you want to do after you post your pictures is take some actual measurements of your model. So the first thing I measured was this side down here. And then I'm going to draw a triangle on this model, right? And then, because we know how to prove triangles are similar, right? We've spent a lot of time doing that. So then I'll label my triangle ABC. So when I measured side BC, that was 15.9 centimeters. Well, when I compare that to the actual height of the Eiffel Tower, which is 124.9 meters, I get a ratio of 7.86. Okay, so then I found the midpoint of side BC, which is right here, and I called that point M. Then I measured from point M to the top of the Eiffel Tower model, and I found that that was 42.5 centimeters. Well, when I took that ratio, I actually got a different value. When I took the ratio of the height of the actual Eiffel Tower, which is 357.5 meters, and took that over the height of my model, which is 42.5 centimeters, I got 8.41. Well, that's a different ratio than before. So this is going to be the first change that I make. Is my model similar to the actual monument in every way? No, it didn't really even meet the basic requirements, which is that the base width and height are similar. And so which parts of your model are not similar to the actual monument? The height. And so how did I change it? Change the height to 45.5 centimeters. Now, how did I get that number? Well, I took the height of the actual Eiffel Tower, 357.5, and I divided by this ratio up here, 7.86. And when I did that, I got 45.5 centimeters. Okay, so now when I do 357.5 divided by 45.5, I get that same ratio of 7.86. Okay, And so then the next thing that I do is I assume, the next thing that I do is I start my flow chart. So the ratio of the base of ABC is 7.86, and the ratio of the height of that triangle ABC is 7.86. And then I just sort of, my proof is I just show my math for how I got 7.86. Or my evidence for that is I'm just showing the arithmetic. Okay, and so then my next thing is AMB is a 90-degree angle. And I can say that because, well, for one, this is an isosceles triangle, right? Like I know AB is going to be the same as AC, and M is the midpoint. And so I know that this is going to be 90 degrees right here. This is kind of a little bit of an assumption. You could make assumptions in your proof here. I'll tell you if your assumptions are not valid when you turn it in, and let you make corrections or help you prove your assumptions if that needs to happen. So I know that AMB and AMC are both 90-degree angles, so I know that these two are both going to be equal or congruent. And so then that's my next piece, is AMB is congruent to AMC, and that's because they're both 90 degrees. And so up next I'm going to be using Pythagorean theorem to show that these hypotenuses of triangle ABC, to show that those hypotenuses are the same. So we'll start with AB. So I know that's going to equal BM squared plus AM squared. So BM is here and AM is here. Okay, so I'm gonna square those two values. BM, that's just half the base, so half of 15.9, that's 7.95. AM, well, that's just going to be the height, which is 45.5. Square those two values to get AB squared, and then I add them together and take the square root, and I get 46.2 for AB. And then when I calculate AC, it's going to be the exact same calculation. I'm taking this length squared plus this length squared, taking the square root to get AC. Okay, and so then now I'm going to do the same thing, but for the actual Eiffel Tower. So all this math up here was to get the lengths of AB and AC on my model. Now I'm going to get AB and AC on the actual Eiffel Tower. So I'm going to use half of the base. So that was 124.9. I'm going to use 62.45. Square that and add it to the height squared, which for the actual Eiffel Tower is 357.5. Square them, add them together, take the square root. AB ends up being 362.9. And AC will also be 362.9. Okay, so then now I can take AB on the model and put it over AB on the, I can take AB on the monument and put it over AB on the model to get the ratio of the hypotenuse. So 362.9 over 46.2, well, this also ends up being 7.86. Okay, so I can say the ratio of AB equals 7.86. I'm getting that by dividing 362.9 over 46.2, that's 7.86. Now, I also use Pythagorean theorem in here to get the values of AB for each of those. So really, this is actually two steps. If you do this on your actual flowchart proof, I am going to mark you down a little bit. So this is sort of an example of a mistake that you might make. I'm not going to mark you down a ton, though. Right? This is something that you're not supposed to do because this is really two steps. You can tell because I've got kind of two different pieces of information to prove it here. But I just wanted to give you an example of something that you can do if you're sort of unsure and okay taking a little bit of a hit just to make the proof a little bit easier. Okay, and so then we can do the same thing with AC, right? show what the ratio equals, and then use Pythagorean theorem. Right, so those are the two hypotenuses of the triangle. Well, now we've got three side triangles. We've got the base, which is really BC. We've got AB, and we've got AC, and all three of those sides are similar. So now we can prove that the whole triangle ABC is similar, because since three sides are similar, it is going to be similar by the side theorem. Okay, so we've got our Eiffel Tower here. So let me draw sort of like a square around the base. And we're sort of using this side right here to prove that this whole side of the triangle was similar to the actual Eiffel Tower. Well, now let's prove this side is similar. Well, it turns out when you make the measurements of that side, they're the exact same as this side. It's the same measurements. So how are we going to prove that they're similar? Well, it's going to be the exact same proof. And in fact, the ratio of the base for this one is 7.86. The ratio of the height is 7.86. And the ratio of the hypotenuse is again 7.86. The only thing that's different is we're looking at a different side of the triangle now. Now instead of ABC, it's ACD. But really all we're going to do is use that exact same proof here, and we're just going to change the letters. So the ratio of the base of ABC, well, this isn't ABC anymore, now it's ACD. Same thing with the height, instead of ABC, now it's ACD. The angles, instead of AMB and AMC, it's going to be AMC and AMD. And then the hypotenuses, instead of AB and AC, it's going to be AC and AD. And so then now we've proven that the side of triangle ACD of the model is similar to the monument. And again, it's by the side theorem. Well, you don't actually even have to rewrite your flowcharts for each side. If the sides are similar, you can just, if the faces are similar, we can just say that they are by symmetry. And so that's what that's sort of the way I write it here, is side ACD of the model of the Eiffel Tower is similar to the actual monument. Right, and we can do the same thing for this side right here, side ADE. So side ADE of the model of the Eiffel Tower is similar to the monument, and again, this is by symmetry to side ABC. Right, so I'm just saying that these next three sides are similar because they have symmetry to the original face that we proved was the same, which is ABC. And so then there's one more side, ABE. Side ABE of the model of the Eiffel Tower is also going to be similar to the monument, and that's again by symmetry. Okay, so think about your model, right? Think about which sides of your model are going to be, or which faces of your model are going to be symmetrical. Right, and so then that should break it down a little bit in terms of what you actually have to prove, right? Like if your model is sort of pyramid shaped, kind of like mine, you don't have to prove that all four sides of the pyramid are the same. You just have to prove one is, and then you can say that the other three are by symmetry. Okay. All right, so then up next is that you just got to prove that the base is similar. This is going to be an easier proof. So BC, we already showed that had a ratio of 124.9 over 15.9, so that's 7.86. Same thing with CD. And it's important to note that BCDE is a quadrilateral, and you haven't really learned how to prove quadrilaterals are the same yet. I'm going to show you a real easy method right here. So one way to prove that quadrilaterals are the same is if you show that two adjacent sides are the same. Okay. So what you want to show is that two adjacent sides are the same. Now it's important that they're adjacent. Remember, that means next to each other. So you don't want to use two sides that are opposite from each other. You want two adjacent sides and show that they're similar, right? So that they have the same ratio. So that's what we've done so far, is BC and CD are similar, right? And it could be any two adjacent sides. So it could have been CD and DE, right? But I chose BC and CD. Those two are similar. And then you need to show that three angles are congruent. Oh, here, let me go. Slideshow view. There, that's better. So then we need to show that three angles are congruent. Now the reason why it's three is you need to show the reason why it's three is because if three angles are the same, that means that all four angles are the same. So essentially it's two adjacent sides and three angles. Okay, well, if you use a protractor, you can measure, because these are made with blocks, that these angles are all right angles. So I've got that my two sides have the same ratio. Now let's do this angle right here, BCD. That angle is 90 degrees. And so that's true on both the model and the actual monument. So angle BCD of the model is congruent to the monument, and that's because they're both 90 degrees. Well, I can say that about any of the four angles on here. So I also use CDE and DEB. CDE is 90 degrees, and DEB is 90 degrees. And so all of those pieces of information together tell me that the quadrilateral BCDE of the model of the Eiffel Tower is similar to the monument. And so that's the base. I'm proving that the base is similar to the monument. And that's because two adjacent sides and three angles are similar. So this should be something new. Two adjacent sides and three angles. If you can prove that those are similar, you can prove that the shapes are similar. And similarly, if you can prove that two adjacent sides are congruent and three angles are similar, then you can prove that the quadrilaterals are, if you can prove that two adjacent sides and three angles are congruent, then you can prove that the two quadrilaterals are congruent to one another. Okay, so is your model actually similar? Explain why or why not. Well, mine's actually a no. Even after changing the height of my model, it still isn't completely similar to the actual monument. That's because there are other dimensions, like the width of the platforms, and I'll show you what I mean by that, that are still not scaled to the actual monument. So think about my picture. I drew a triangle on here. Well, you can definitely see how the side of the Eiffel Tower is triangular, but a triangle really isn't that great of a shape to model the side of it. Look at all this space over here, right, and over here, right? It would be much better if I took the side of my model and broke it up into smaller shapes, kind of like this, right? So now I've got a trapezoid here, I've got a trapezoid here, and I've got a triangle here. It's still not perfect, but this is a much better model for the side of my monument. But the problem is even if I tried to do this, I would need to make more changes on page 2, because ED or BC, that's what I mean when I say the platforms, so ED or BC, well, those platforms are not of that same ratio that they're supposed to be, right? They're supposed to be 7.86 is that ratio from the actual monument to the model, well, that's not really the same ratio as what my model of the monument is. So I would need to make some changes there for them to actually be 100% similar. So that's sort of what you want to think about as you're doing this. One last note, how would you take a trapezoid and actually prove that it's similar? Well, you can take a trapezoid and break it up into three shapes that we know how to do. So here I've taken EDFG, or sorry, it's FEDG. So here I've got FEDG. Oh, sorry, no, it's DEFG. Sorry, forgetting my alphabet. DEFG, I've got that quadrilateral, and I'm going to break that up into three shapes that I know how to prove are similar. And that's just by drawing some lines down here at 90-degree angles. And so now I've got two right triangles. That should be pretty easy to prove that those are the same. And then I've got a quadrilateral in the middle here, which you've just learned how to prove quadrilaterals are, how to prove that those are similar. So, first step, or the first steps that you should take for proving that your model is similar here. You should take some pictures of your model, and then you should try to break it up into simple shapes that you can prove are similar or not. Right? Do some searching on the internet, try to find the dimensions of, different parts of your model to prove that they're similar. And if you need any help with any of this, feel free to reach out. I'm more than happy to WebEx with you and help you get started and, get going on the process of proving that your model is similar. And then one final question. After you've done all that, you're going to answer the question, is your model congruent to the monument? And you're going to explain why or why not. So just kind of like you did with similar, you'll do the same thing with congruent. I'm not going to tell you how to do this one. This one I want you to kind of figure out on your own, but this will be the absolute last thing that you do. Yeah. Okay, let me know if you have any questions.